Ancient people saw them as messages from the gods, as supernatural winds that blew from the realm of spirits. Modern science has linked these polar light shows, called auroras, to vast waves of electrified gas hurled in our direction by the sun. Today, researchers from a whole new generation see this dynamic substance, plasma, as an energy source that may one day fuel humanity's expansion into space. What can we learn? And how far can we go? By tapping into the strange and elusive fourth state of matter. A small cadre of scientists has come to Fairbanks, Alaska, to realize what may seem an impossible dream: to revolutionize space travel. Dr. Ben Longmire and his team from the University of Michigan have designed a whole new type of rocket engine that promises a faster and more efficient way to get around in space. They're here to test components of this rocket by sending them aboard helium balloons to an altitude of 30 kilometers into the harsh environment of space. Above the North and South Poles, conditions are about as harsh as you can get. Our planet is bombarded with a steady stream of charged particles from the sun. Earth's magnetic field accelerates and channels them, turning the night into a spectacle of color. While most astronauts train to live and work in zero gravity, or to move around in bulky spacesuits, these would-be space explorers are preparing to negotiate some of Earth's harshest environments. Once they launch their payload, it will rise slowly into the upper atmosphere. After drifting through the night, above 99% of Earth's atmosphere, the payload will detach from the balloon and parachute down to the ground. The team must be prepared to retrieve it across a large stretch of Alaska's snowy wilderness. To understand the revolutionary nature of the idea they are pursuing, we go back to the dawn of rocketry. In over 100 years, the technology of a rocket has hardly changed. Fill a cylinder with volatile chemicals.
Contact! Yes, contact!
Then ignite them in a controlled explosion. The force of the blast is what pushes the rocket up. Nowadays, chemical rockets are the only ones with enough thrust to overcome Earth's gravity and carry a payload into orbit. But they're not very efficient. The heavier the payload, the more fuel a rocket needs to lift it into space. But the more fuel a rocket carries, the more fuel it needs. One of the fabled Saturn V rockets of the Apollo era, for example, weighed in at 177,000 kilograms. Filled up with fuel, it weighed almost 16 times that. The space shuttle, with maximum payload, weighed about 100,000 kilos. Add tanks and fuel, and it lifted off at 2 million kilograms. Regardless of weight, for a spacecraft to escape Earth's gravity, it must reach a minimum speed of 40,000 kilometers per hour. The energy needed to do that meant there wasn't enough fuel for a sustained acceleration to more distant planetary shores. Most missions beyond Earth have relied instead on their initial launch speed to coast to their destination. The twin spacecraft of Voyager, for example, did not have enough speed to reach their current positions at the edge of the solar system. To give them a boost, flight planners sent them into Jupiter's gravitational field, using its pull to slingshot them out to Saturn. Voyager 1 used Saturn to accelerate to almost 63,000 kilometers per hour. Voyager 2 got further assists from Saturn and Uranus. Ben's rockets promise far greater gas mileage than traditional chemical rockets, but with enough power to reach distant targets more quickly. The idea is that once in space, his rockets use electricity to create a weak force, which over time can accelerate them to very high speeds. They run on the same fuel that nature uses literally to power the cosmos. Not long after its explosive beginnings, the universe was awash in vast stores of hydrogen gas. But even as the universe continued to expand, gravity drew clumps of matter into ever denser concentrations. The earliest stars took shape, immense balls of hydrogen gas hundreds of times the mass of our Sun. As they contracted inward, they heated up and ignited. Intense radiation now began to flow through the voids. That had the effect, all through the universe, of stripping electrons away from the primordial gas. The universe became filled not with solids, liquid, or gas, but with a fourth state of matter, plasma. On our planet, plasma occurs only in rare circumstances. In a hot flame, a bolt of lightning, or in a blown electrical transformer. Made up of negatively charged electrons and positively charged ions, plasma is in most cases electrically neutral, since the charges balance each other out. That led the physicist Erwin Langmuir in the 1920s to compare it to the clear liquid plasma that carries blood cells through our bodies. The development of radio led to the discovery, high above the Earth, of a natural plasma ceiling, the ionosphere. It hovers above us, reflecting some radio frequencies and absorbing others. Its importance became clear when engineers noticed that radio waves could, under some conditions, travel beyond our line of sight. They discovered that signals could be bounced deliberately off this conducting layer in what's called skywave propagation. In World War II, a whole new age of global communications came of age when radio was used to execute complex worldwide logistics of troop and ship movements. The presence of the ionosphere is due to a steady stream of charged particles, or plasma, that comes from the sun. A spacecraft with complex computer components must be able to survive constant exposure to these particles. As part of their design process, Ben and his team want to test some of the specialized components of their rockets in the plasma-filled environment of our upper atmosphere.
Got it down. I think it's just the sun.
Yeah, I think that one's okay.
Alright, yeah. I'll wrap the middle one though. Or I can just wrap it.
These components will be mounted on a simple frame attached by rope to a high-altitude balloon.
Hold on, they're not oriented the same.
The frame is also outfitted with an array of novel sensors to take independent readings. One holds a colony of bacteria.
The idea is that the bacteria itself can detect radiation. So it mutates in a certain way or in a very known way that when you send it into an environment with a lot of cosmic rays and a lot of perhaps X-rays from the aurora itself, it mutates. And so we'll detect sort of the level of radiation that it's exposed to by looking at these mutations after we recover the bacteria from flying it to the edge of space in these balloon capsules.
Jordan, you got the camera or wait a second.
Another is a series of tiny GoPro cameras converted to record the intensity of infrared and ultraviolet light, normally hidden from the human eye.
We want it to kind of puff up so we know it's replaced all the air.
The team uses argon gas to insulate instruments against the cold, with chemical packets added for warmth.
So this test, we're going to be doing normal video, version 70 firmware.
They stabilize the frame with tiny gyroscopes and outfit it with GPS devices for tracking.
Cool.
This team is doing much more than just designing instruments to survive a rain of charged particles. Their goal is to design spacecraft that actually harness the explosive properties of plasma. Unlike most matter on Earth, plasma conducts electricity and responds to magnetic fields. In space, these properties influence the formation of structures like galaxies and nebulae. and they play a role in some of the most violent processes in the universe, such as the formation of a black hole, It forms in the wake of a giant star's death, when matter collapses into its core. It swirls in along what's known as an accretion disk. Magnetic fields take shape on the disk, rising and twisting around the polar regions. They draw huge volumes of plasma up, then shoot it out at high speeds. These plasma jets can extend far beyond the largest black holes. You can see them blasting continuously from the centers of galaxies, reaching thousands of light years into space. Studies of one giant nearby ball of plasma show what a complex and volatile substance it can be. In the core of our sun, high heat and crushing pressures cause hydrogen atoms to crash together. That sets off a nuclear reaction in which hydrogen atoms fuse into heavier ones like helium and carbon, generating heat. This heat slowly rises to the surface of the sun in vast plumes of plasma. You can see evidence of this process, called convection, in a pattern of ever-evolving blobs known as granules. They are like the tops of thunderstorms. Even as energy builds within, the sun's gravity and density can stifle its escape. What carries it out are magnetic fields. They twist and wrap around, channeling energy to the surface. The fields can power immense loops of hot gas, about 60,000 degrees Celsius, then rise up from the solar surface and fall back. The largest eruptions, called coronal mass ejections, can reach up to 3 million kilometers per hour as they hurtle out across the solar system. They can literally slam into Earth's own magnetic field. Because solar particles are charged, a portion follows the orientation of Earth's magnetic field lines. Finding an opening at the poles, they race down into the atmosphere. You know this is happening when you see the beautiful lights of the aurora borealis in the far north, or the aurora australis in the south. They appear when charged solar particles collide with oxygen molecules in the upper atmosphere, causing them to glow blue, red, and green depending on altitude. Flying through a zone called the thermosphere, some 350 kilometers above the Earth, astronauts in the International Space Station watch in awe as the aurora shimmers, framed by the glow of stars and cities at night. Back in Michigan, Ben and his team have set up a lab to pioneer a whole new generation of plasma rocket engines. The lab recalls an earlier period of space exploration. It features a giant vacuum chamber built in the 1960s in hopes of winning a contract to test Apollo moon rovers.
As part of all the facility upgrades that Roland has done for the X3, some of these should be able to...
The chamber has given this small university team the ability to accelerate their research into the physics of plasma and rocket engine design.
The tubing for the gas lines don't affect the thrust measurement. So by having these extraordinarily flexible wires, these wires...
They are actually part of a larger community of plasma rocket scientists within NASA and within private companies like Ad Astra of Houston, Texas. Because plasma does not occur naturally on Earth, the challenge is to create it, then harness it. The teams inject a gas, commonly argon, into a chamber. They bombard it with radio waves, which strip electrons from the gas and turn it into a plasma. The soup of electrons and ions accelerates as it moves through a magnetic field generated by superconducting magnets. A second radio blast heats it up to 1,000,000 degrees Celsius. That's enough to blast it out and propel a spacecraft. The idea of using plasma to power rockets is not a new one.
Over here?
Yeah.
Okay. 3, 2, 1.
Go! No spin, look at that.
The Polish physicist Stanislaw Ulam is said to have been inspired by atom bomb tests in the 1940s. He speculated that waves of plasma from small nuclear detonations could propel a spacecraft to extreme speeds. In the 1950s, that idea animated dreams of exploring the solar system in spacecraft like this 360-ton Mars-bound vehicle. The idea gained funding in the Orion project, with the idea of driving a spacecraft with nuclear pulses and landing on Mars in only a month. Concerns about radioactive exhaust helped doom the project. Plasma rockets, energized by nuclear reactions, were revived in the Daedalus and Nerva projects of the 1960s. And again at the beginning of this century, as part of a proposed journey to Jupiter's moon Europa. Rising costs killed that mission. Newer plasma rocket concepts have switched to solar energy to power their engines. Among the most ambitious, the Dawn mission was sent into orbit aboard a Delta II rocket in the year 2007. It then headed out on a 10-year mission to the asteroid belt. It uses only about 10 ounces of xenon gas fuel per day. With engines designed to fire for over 2,000 days, over time, it is expected to gain an additional 38,000 kilometers per hour. After a gravity assist from Mars, Dawn arrived at the asteroid Vesta in 2011. It spent a year mapping its surface and seeking clues to its interior structure. Now headed for Ceres, a dwarf planet located within the asteroid belt, Dawn will be the first probe ever to visit. Made up of rock and ice, Ceres may well have an internal liquid ocean. It takes us back to the formation of the solar system, when objects like this grew and developed into planets. Long-range missions like Dawn are just one of many uses for plasma rockets.
So NASA launches spacecraft with ion engines and Hall thrusters on board. Almost every new geostationary satellite that a company will invest in and put up in orbit will have some sort of electric propulsion device on board to do station keeping, so to do little changes in attitude and maneuvers to keep it in its geostationary orbit.
NASA is planning to use a plasma rocket to do some even heavier lifting as early as 2016. Flying at an altitude of 350 kilometers, the International Space Station whips around the Earth every 1.5 hours. To stay aloft, it must maintain a speed of 28,000 kilometers per hour. But its solar panels and crew modules smack into so many tiny molecules in the upper atmosphere that it gradually slows down and loses altitude. To stay aloft, the station uses up around 4,000 kilograms of fuel per year. That fuel must be flown up from Earth, which in turn reduces the amount of food, water, people, and equipment that a resupply mission can deliver. The idea is to use a plasma rocket to help boost the station to a higher altitude, powered by electricity generated by solar panels aboard the station. Plasma rocket builders like Ben hope to one day scale up the technology to power a long-range human mission. After weeks spent accelerating in Earth orbit, the rocket would make a break for Mars, cutting flight time from a year to several months would lower costs and crew hazards. In the meantime, Ben has his sights set on what he sees as an even larger revolution in space exploration. Using plasma rockets to power a fleet of miniature spacecraft. Ben's rockets are so small that they can fit into your carry-on luggage.
So here we have a CubeSat. This is a small spacecraft. Its total mass would be something on the order of 5 kilograms, so it's about 10 pounds. It's 30 centimeters by 10 by 10. This is considered a 3U spacecraft, so 3 units of 10 by 10 by 10. And we'd like to send this small spacecraft up with one of our new propulsion elements in it. This is a rapid prototyped propellant tank. So we would use this tank to store our propellant. Initially, we have an idea to use a very simple propellant.
The NASA craft Dawn uses the inert gas xenon as fuel. Ben's team has turned to another type of fuel that's more compact, can store more energy, and is less volatile. Distilled water.
We'll ionize that propellant with radio waves, and that'll form a plasma. So we'll strip off some electrons. We'll have this sea and collection of ions and electrons. We then accelerate, we superheat that plasma, and then we accelerate it through a magnetic nozzle. So the plasma never touches a material boundary, so it doesn't cool off. All of that would be contained within this spacecraft. So the propellant tank is designed to be the right size and dimension, and we'd have a propulsion module within the CubeSat itself. This is an early prototype circuit board, just this component that would sit inside of the CubeSat, and it would take the DC power from some sort of solar panel on the surface, change that DC power into our radio waves that we need to ionize the propellant into a plasma. We then shoot this plasma out the back, and we apply just a little bit of force. It's not a whole lot. It's something like the force of a sheet of paper sitting in your hand. And because there's very little drag in space, we use this small amount of force applied over a very long amount of time to accelerate to very high velocities with the spacecraft. And so if we do that, we can send these little micro spacecraft, nanosats, we can send them to places like the moon, we can send them to Mars, and someday we'd like to send them even as far as Jupiter and maybe put some little sensors on board and be able to detect possible life on some of these moons out near Jupiter and Saturn. So instead of a $1 billion NASA mission to explore the moons of Jupiter, we can get away with something like a $1 million spacecraft mission with one of these small sats. And so that's the real advantage, being able to have a very low barrier to entry financially and technologically to make some of these innovations really quickly, go fly them, go fly often, and make these discoveries.
Already, hundreds of micro, nano, and even smaller satellites are in orbit. They get into space by piggybacking on commercial or government launch vehicles. Their missions range from communications and intelligence to Earth imaging. Because the cost of building them is so low, the number of tiny satellite missions is on the rise.
Yeah, there was no other satellites up there.
With an array of plans already materializing, the team is tapping into satellite traffic and orbital communication systems.
Looks like we won't quite go over to the ground station here.
Ben and his team plan to start with a series of orbital missions, then to go interplanetary.
So you can see here some of the technology we're working on. So this
Ben
is
imagines that his little group could take center stage in a project that space visionaries have long seen as essential to the quest to extend our eyes and minds across the solar system.
Guide the plasma out through a magnetic nozzle. Recently, we also envisioned that a large cadre of these small spacecraft could form what would be an initial interplanetary internet. So you can think about a large number of these spacecraft orbiting the Earth, orbiting the Moon, being spread out between the Earth and Mars, and providing little data relays between all of those positions so we can get a lot of data back and have the beginnings of a real solar system internet going beyond the Earth.
Well, as long as it's beeping like that, you have to shorten it to get into the grove.
Back in Alaska, their latest payload has flown all night at an altitude of over 100,000 feet. Then, in the low air pressure, the balloon burst and the payload parachuted to the ground.
Point at it.
Yeah, so this is our Garmin GPS. We've got a waypoint.
From GPS signals given off by the payload, they have a good idea of where it is.
We've plugged in the coordinates. And this is going to be an all-day adventure. It sounds like we've got 5 miles.
But that doesn't mean retrieving it will be easy.
It's going to be rough going at
No,
the
we're
end.
right here. And you see where it says Sled Road?
Yeah.
That's the trail we're going to be following down.
Oh, wow.
John knows where there's a cutoff that's going to take us off that Sled Road over to Dune Lake. And this little pond or lake right here, just to the west, maybe about a mile north, is where we believe the target is.
The payload to be, yeah.
So we're going to come down here, we're going to look for the turn, head out to Dune Lake, and then we're going to be off trail from here all the way up to here.
Wow, okay.
It's about 5 miles.
All right. And then we're going to have, both Hans and I have these GPS locator devices. So we've got our first payload, Aurora 1, that we're going to go recover and track. We are going to use these snow machines to recover. We've got 2 expert guys that go track these for a living, sort of. One guy's a retired helicopter military pilot. And we've got GPS units, all the coordinates plugged in. We're about 26 miles from here as the crow flies. We're about 35 miles by trail, last 5 miles being really off trail, so we're gonna have to break some new trail.
The plan is to navigate well-worn snow trails and get within striking distance. But if the payload has landed away from the trails, they'll have to brave wilderness landscapes and deep snows.
Payload is marked with that dot.
Oh, so we are heading down south. We are on this road.
We're heading north.
It takes nearly all day to get to a point about 7 miles from the payload. Team members set out across hills and ravines. They get to within 2 miles. With time running out, they turn around.
It was too far away still to snowshoe in and snowshoe back and get back before dark. Not going to happen today. We're going to go back, recoup, probably send a skeleton team down tomorrow and try for a second recovery. Really disappointing we couldn't get there. You know, I feel like we're so close. This thing came 50 miles from the initial launch site. It was floating around in the atmosphere for 10 hours.
Right, I know.
And you know, it's so frustrating just to get within 2 miles.
The next day, a long hike on snowshoes finally gets them to the payload. Later on, they'll say it was worth the effort. One of Ben's goals is to help boost a whole new approach to space travel that's now emerging. May 2012 marked a major milestone in the rise of free enterprise in space. The SpaceX company successfully docked an unmanned space capsule with the International Space Station. It followed that up 6 months later with the first commercial resupply mission.
And launch of the SpaceX Falcon 9 rocket as NASA turns to the private sector to resupply the International Space Station.
That's just the beginning. NASA is looking to companies to supply orbital launch services and to be long-term partners in future manned missions beyond the moon. Hoping to make big bucks, companies are developing orbital habitats and space planes, laying the groundwork for missions geared to mining, exploration, and even tourism. To Ben, this new race to space will go to the swift and the innovative. Today, because of weather and winds, he and his team have chosen to launch their payload from the spectacular Ruth Glacier in Denali National Park. Amid the rugged terrain, this immense river of ice sweeps down into a perfect natural runway. The payload and frame have been pre-assembled. The team makes a few last-minute adjustments. They inflate the balloon with helium gas. With dusk approaching, balloon and payload are ready.
Beautiful sight.
Got positive buoyancy. Both GPS devices are on and locked. Last camera check. Do a pan of the team.
Off it goes. The balloon drifts up through the dense polar air. With night falling, it rises up to the edge of space. Meanwhile, overhead, a solar storm is raging. Aboard the International Space Station, astronaut Don Pettit is making observations to complement what Ben's team finds. He passes over the Arctic several times during the balloon's flight. The auroras he photographs are an indicator of the amount of solar particles that will pummel Ben's rocket components. This is a time of high solar activity, approaching the peak of an 11-year cycle. The Arctic Circle is framed by a ring of dancing auroral lights. Curtains of green and red and blue drape our planet's graceful curve. This university-based experiment operates on the remote edge of modern science, dominated by large international projects such as the Hubble Space Telescope, the International Space Station, or the Large Hadron Collider.
So this technology that we're trying to miniaturize is significant in the sense that it sort of opens up new frontiers in the same way that miniaturizing computer technology to a point where it fits in your pocket. So everyone carries around a cell phone. They have these miniature computers. It does a lot of data processing. It gets you to your destination by GPS. That sort of technology didn't exist 20 or 30 or 40 years ago when you had these big mainframe computers that were at national labs. So we're trying to change the paradigm of space exploration from the national lab case to the cell phone case, the miniature case, to be able to do a lot more things and improve our capability as a species.
Working small, Ben's team believes they are onto something big. Their goal is not only to open new avenues of space exploration, but to actually seize the initiative. It's a romantic idea of individuals challenging the odds and striking out to new frontiers. With technologies that are getting smaller and more powerful, the obstacles to private space exploration appear to be falling. Who will hold back this new breed of explorer?